Hi, I'm Li Mingjiang, a PhD student from S-Lab, Nanyang Technological University. I present our paper, Deceive, Adaptive Pseudo Augmentation for GAN training with limited data. While state-of-the-art GANs like StarGAN2 are constantly pushing forward the fidelity and resolution of synthesized images, they usually require a large amount of training data to fully unleash their power. Training GANs with insufficient data tend to generate poor quality images. As shown in this figure, StarGAN2 synthesized results deteriorate given only thousands of images on various datasets, such as human faces, cat faces, and anime. Collecting sufficient data samples for contemporary GANs is sometimes infeasible, especially in domains where data are sparse and privacy sensitive. To ease the practical deployment of powerful GANs, it is necessary to devise new strategies for training GANs with limited data while preserving the quality of synthesis. We analyze the underlying cause that impedes the effective GAN training on limited data and draw consistent conclusions with some recent studies. In this figure, we show the training snapshots of two StarGAN2 models on the FFHQ dataset. The settings of these two models differ only by the amount of training data available to them. As can be observed, both training processes start smoothly, and distributions of discriminator outputs for the real and generated images overlap at the early stage. As the training progresses, the discriminator only has access to limited data, experiences diverse predictions much more rapidly, and the average sign boundary turns out to be more apparent. This divergence in prediction shows that the discriminator becomes increasingly confident in classifying real and fake samples. Meanwhile, the evaluation FID scores deteriorate, consistent with the divergence of discriminator predictions. These phenomena demonstrate how a discriminator gets overfitted quickly under limited data. The overfitting of discriminator impedes the generator's convergence, rendering severe instability of training dynamics. Its feedback to the generator becomes less informative. Consequently, the generator converges to an inferior point, compromising the quality of synthesized images. Many recent studies propose to apply standard data augmentations for GAN training to enrich the dataset diversity to mitigate the overfitting of the discriminator. For instance, Adaptive Discriminator Augmentation (ADA) adopts data augmentations to both real and generated images, and it further devises an adaptive approach to control the strength of augmentations. Our work extends the study of such an adaptive approach. Meanwhile, our method does not rely on any external augmentations that require certain computational costs. Another type of solution is model regularization. Previous relevant strategies on regularizing GANs are designed for various goals, either for stabilizing training or preventing mode collapse. Under the limited data setting, a very recent study proposes an LC regularization term to regulate the discriminator predictions using two exponential moving average variables that track the discriminator outputs throughout training. Compared to model regularization, our method is more adaptive to fit different settings and training status without manual tuning. Addressing the discriminator overfitting is still an open problem. We thus provide an alternative way from a different perspective, which is also complementary to standard data augmentations for gaining a further performance boost. We propose a simple yet effective method called Adaptive Pseudo Augmentation (APA). In GANs adversarial training, the goal of the generator G is to deceive the discriminator D and maximize the probability that D makes a wrong judgment. Therefore, G keeps refining its generated samples to better deceive D over time. When the training only accesses to limited amount of data, one would observe that D turns out to be overly confident and hardly makes any mistake, causing its feedback to G to become meaningless. We found that the generator itself naturally possesses the capability to counteract discriminator overfitting. We employ a GAN to augment itself using the generated samples. Specifically, our method takes the fake or pseudo samples synthesized by G and moderately feeds them to the limited real data. Such pseudo data are presented to D as a real instance. The goal of this pseudo augmentation is not to enlarge the real dataset, but to suppress the discriminator's confidence in distinguishing real and fake distributions. However, blindly presenting the fake images as reals to D may weaken the fundamental ability of D in adversarial training. To moderate the deception, we perform the pseudo augmentation based on a probability P that quantifies the deception strength. We know that the overfitting state of D is dynamic during training. It is intuitive to let the deception probability P to be adjusted adaptively based on the degree of overfitting. To quantify overfitting, we study a series of overfitting heuristics, lambda, derived from the discriminator raw output logics. Applying the overfitting heuristic, the deception strength P can be adaptively controlled without manual tuning, regardless of data skills and properties. We provide 3 plausible variants of the overfitting heuristic lambda. Here, lambda R estimates the portion of real images that obtain positive logic predictions by D, and that of generated images is captured by lambda F. Besides, lambda RF indicates half of the distance between the signs of the real and fake logics. For all these heuristics, lambda equals to 0 represents no overfitting, and lambda equals to 1 means complete overfitting. We use lambda R by default. During training, P is adjusted adaptively according to lambda. We initialize P to 0 and set a threshold value for lambda. If lambda signifies too much or little overfitting regarding the threshold, that is to say, larger or smaller than the threshold, we will increment or decrement P by one fixed step and climb it from below to 0. We also provide a theoretical analysis of the proposed APA and connect it with minimizing the JS divergence between the smooth data distribution and the generated distribution, proving its convergence and rationality. Details can be found in our paper. Then, let's briefly go through some typical experimental results. We show the effectiveness of APA on various datasets with limited data amounts and the comparative results by state-of-the-art GAN2. The quality of images synthesized by GAN2 degrades under limited data. Ripple artifacts appear on the cat faces and human faces, and the facial features of the animal faces are misplaced. On the bird dataset with heavy background clutter, the generated images are completely distorted, although trained with more data. The proposed APA significantly ameliorates image quality on all these datasets, producing much more photorealistic results. Here are comparative results on subsets of FFHQ with varying amounts of data. APA improves the image quality in all cases. Notably, the quality of synthesized images by APA on 5K and 7K data is visually close to StarGAN2 results on the full dataset, while with an order of magnitude fewer training samples. We further provide the overfitting and convergence analysis of APA compared to StarGAN2 on FFHQ. The divergence of StarGAN2 discriminator predictions can be effectively restricted on FFHQ 7K by applying the proposed APA. The curves of APA on FFHQ 7K become closer to that of StarGAN2 on FFHQ 70K, suggesting the effectiveness of APA in curbing the overfitting of the discriminator. Besides, APA improves the training convergence of StarGAN2 on limited data, shown by the FIDK curves. We compare the proposed APA with other state-of-the-art solutions designed for GAN training with limited data. LC regularization slightly improves the synthesis quality of StarGAN2 by reducing distortions on the images. The amelioration of visual quality is more evident by applying ADA, where the ripple artifacts are clearly subsided, while some minor artifacts exist on hair and beard. The proposed APA achieves comparable or even better visual quality than ADA. Notably, APA is also complementary to ADA for gaining a further performance boost, suggesting the compatibility of our method with standard data augmentations. We also compare the computational cost of APA against ADA. There is no parameter or memory increment for both methods. The average training time we present here indicates the advantage of the proposed APA on negligible computational cost. Here are some higher resolution examples to further illustrate the effectiveness of our approach in improving StarGAN2 with limited training data. Finally, we present additional training convergence visualizations on FFHQ 7K. The proposed APA effectively improves the training convergence of StarGAN2 on limited data. For more details, such as quantitative results, performance on big GAN, and ablation studies, please refer to our paper and supplementary material. Our code will be made publicly available. Thank you for watching.